Good morning, professors. I'm Chang Guo from Taipei Medical University. Today, the topic I'm going to present is involving dengue fever prediction by incorporating novel air quality indexes with random forest. It is related to national prediction model for dengue fever and the first time to make prediction model incorporating air quality indexes in Taiwan. There are 4 parts in this presentation: introduction, materials and method, results, and discussion. The first part is introduction. Dengue virus transmissions are the main issue in the tropical and the subtropical countries. The intensity is limited by the change of weather and the climate. According to the previous studies, there are 390 million dengue infections per year in the tropics, of which 96 million appears as significant infection. Another study also pointed that dengue occurred in 128 countries, about 3.97 billion population at risk. In Taiwan, there are several severe outbreaks which happened in the last century. In the recent, some severe outbreaks also occurred in Taiwan. There are 3 severe outbreaks during 2010 to 2015. In 2010, the main infectious area is Penghu County. The prevalence rate is 101 per 100,000 population. In 2014, the main infectious area is Kaohsiung City. The prevalence rate is 540 per 100,000 population. It exceeds more than 2 times of national prevalence rate. The main infectious area is Tainan City in 2015. The prevalence rate exceeds more than 1,000 per 100,000 population. In the previous study, many authors from different countries used many methods to predict many kinds of issues in dengue during 2017 to 2019. These targets include cases, incidence, and epidemic year. Methods include traditional statistical methods and machine learning. Besides, the lag effect is also taken into account. Some researchers point that the lag time of variables that affect the cases or incidence of dengue fever. Therefore, the aim of the study is to predict the occurrence of dengue fever. These variables include the lag date of variables, such as meteorological factor, weather index, and the air quality index. We use blend machine learning algorithms to build prediction model. Finally, I chose the best performance of a machine learning as the prediction model. The second part is material and methods. We used the data from 2013 to 2015, collected from open data of government websites. A total of 805 observations incorporated in the model. Table shows the sources of variable. This data can be downloaded free in the website without permission. In this study, we used two software to analyze the data, SAS and RStudio. There are three algorithms we adopted in this study. I built three prediction models in our environment. Except for logistics regression, random forest and extreme gradient boost are two well-known tree-based algorithms in machine learning. To evaluate the performance of each model, we also adopted four metrics: accuracy, sensitivity, specificity, and AUC. ROC curve plot shows trade-off between sensitivity and specificity. The AUC is the total area under the curve in the diagram. It is a standard indicator ranging from 0 to 1. This figure shows the flow of this study. We divide dataset into two parts randomly: training and test dataset. We use the training set to build the prediction model. Test set is used to evaluate the performance of models. The model with the highest AUC is the best prediction model. We will explain how the variable affect the occurrence of dengue fever based on the chosen model. The third plot is the results. In table, we can figure out that the mean with a significant difference between the occurrence of dengue fever and the non-occurrence. For each variable, the mean of two groups are not equal under the p-value is less than 0.05. This figure shows 16 variables with minimum error in the prediction model based on random forest. This figure is generated by function RFCV, which can reduce the variables sequentially via a nested validation procedures. In this table, the performance of prediction model based on random forest with the top 16 variables selected is better than the one calculated from all variables in terms of AUC and accuracy. In this slide, the figure shows that the random forest of performance is better than logistic regression and XGBoost in terms of all measures. This figure shows the importance of variable. The selected variables are ranked by NDA. NDA is an index generated by observing out-back error for a given variable. NDA index of each variable is averaged to compare others as demonstrated on the x-axis of figure. Daily temperature is the most important variables. The marginal effect generated by partial function in PDB packages are averaged in the plots. The variables are labeled on the x-axis, and the marginal effect is shown on the y-axis. The temperature peaked near 3 degrees Celsius. The probability of occurrence of dengue fever goes higher with higher temperature before 30 degrees Celsius. Every index peak near 5, indicating that marginal effect of UV increase gently before the moderate relative humidity has positive effects and peaks near 17.8. The marginal effect of PM10 is obviously negative to the probability of occurrence. This part is discussion. Our research aims to select your best model to predict the dengue fever occurrence, to find the relationship between predators and dengue fever. From our results, random forest outperforms than other two algorithms in terms of AUC. Temperature is the most important factor to influence the occurrence of dengue fever. The AUC is a great indicator in measuring the performance of the prediction model. Based on results, random forest achieves the highest AUC of 0.9547. Compared to the other studies, the AUC is higher than most of the researchers. Temperature plays a key role in the occurrence of dengue fever. The first author also reported that the effect of temperature showed highly nonlinear relationship on dengue incidence in their generalized activity model. And the second author that also reported that female mosquitoes survive during the temperature ranging 15 degrees Celsius to 13 degrees Celsius. The numbers of offspring peak near 30 degrees Celsius. It might be the risk of the dengue outbreak. PM2.5 and PM10 are two the important air quality indexes. The first also found that there is no relationship between the level of air pollution index and the dengue fever cases. PM10 seems to reduce the occurrence in our results. PM10 is negative correlation with dengue fever cases in the previous study. Although air pollution has not been confirmed by other studies, but it shows obvious influences to the life cycle of Aedes aegypti mosquitoes. The lifespan of mosquitoes and the virus transmission is influenced by relative humidity. The first author reported that the relative humidity is that 1 to 8 weeks ranging from 83.5 to 86 has higher effect to the risk of dengue fever. The second author reported that the rainy season is the peak period of survival of mosquitoes. The limitation of our research is economic of El Nino Southern Oscillation. Many studies figure out that the ENSO is regarded as an important factor influence climate and dengue transmission. Furthermore, transportation, the clustering effect of population density, urbanization, and geography are the factors affecting virus transmission, but these data are difficult to be quantification fairly. In the future, these factors can be taken into prediction model. This part is conclusion. The prediction model built for dengue fever cases or incident rates are used by statistics and machine learning models. Our study aims to occurrence of dengue fever because prediction can be used for epidemic prevention. We consider the lag days of variables to be a prediction model. Our research also can be used to predict the occurrence of dengue fever in few days. Thanks for your listening.